Hello everyone. So today I'm going to talk about the uncountability of the set of real numbers. So we have a theorem that says that the set of real numbers is uncountable. Okay, so we are going to prove it by contradiction. So we suppose that the set of real numbers is countable. So suppose that R is countable. Okay, so now we consider the subset of these numbers, the interval from 0 to 1, so including 0 but excluding 1. So if the whole set of real numbers is countable, then this subset is also countable. So now we consider the ternary representation of these numbers. So we count all of them. So let's say that we enumerated these numbers as the numbers in this interval as x1, x2, x3, x4, and so on. And we consider the ternary representation of them. So they all would start with 0 because they are in this interval. So 0 dot, and then we denote the digits of these numbers as x11, x12, x13, x14, so on. This would be 0 dot x21, x22, x23, x24, and so on. This will be 0 dot x31, x32, x33, x34, and so on. This would be 0 dot x41, x42, x43, x44, and so on. And so on. So now we consider the number y in the ternary representation. We are going to construct the number y in the ternary representation. So we in the same interval between 0 and 1. So we denote first the digits as 0 dot y1, y2, y3, and so on, and we construct these digits as follows. So we demand that all of them are not equal to 2. So y with the index I is not equal to 2 for any index I. So basically we prohibit the digit 2. So in the ternary representation there are like 3 digits, 0, 1, and 2. So we prohibited one of them. So it remains 2 possible digits, 0 and 1 for each of these digits. So now we consider the diagonal in this list of numbers. So x11, x22, x33, x44, and so on. And we we choose digit y1 that is not equal to x11. So x11 is some digit, it could be 0, 1, or 2, and we choose y1 that is not equal to it, because like there are two possible digits remain for y1, 0 and 1. We can always choose like between two possibilities, we can always choose one that is not equal to x11. Similarly, y1 we choose that is not equal to x22, y3 we choose that is not equal to x33, and so on. So we choose these digits that are not equal to this to the digits on this diagonal. Okay, so like to formally write this, so y with index I, we demand that is not equal to x I for any index I. Okay, so it is obvious that we can always choose this digit. So we have like basically two requirements for digits yi, and we have three possible digits. So we can, so two of them are prohibited. We can always choose the third one. Okay, so we constructed this number y, and we noticed that it is not equal to x1 because the first digit yi is not equal to the first digit of x1. So if the number x1 and the number y, they are different in the first ternary digit, okay, therefore they are not equal to each other, right? So x1 is not equal to y. Then similarly x2 is different in the second digit, in the second ternary digit from y. y2 is not equal to x22. Therefore, x2 is not equal to y. And so on, we continue this argument. So we see that any number xi, okay, let's remove the what we don't need. So we notice that any number xi is not equal to y for any index I, because the corresponding digit xii, because of this basically, because the corresponding digit xii, it would be different from the digit yi. So basically this means that the number y that we constructed is different from every number in this sequence. This means that this number y is not enumerated. And this is a contradiction. So now let's discuss one thing. So why did we demand this? Why did we introduce this requirement that yi is not equal to 2? Why did we prohibit the number 2? And the reason for this is that we want to avoid that the number y would end in a sequence of 2's. So if starting from some point all the digits would be equal to 2, so like if we remove this requirement, and if it turns out that all the digits starting from some point would be equal to 2, then this would not be a legitimate representation of a number in a ternary system, because it's just prohibited. Because like if we have a sequence of 2's, this would be equal to like we would need to increase by 1 the previous digit and replace all the 2's by zeros. the same as in the decimal representation, like the infinite, like the number 0.9999 and so on to infinity. So this would actually be equal to 1. Therefore, such decimal representations are prohibited. So this is not a legitimate decimal representation of a number. Similarly, in the ternary system, the sequences ended with like an infinite sequence of 2, they are prohibited. So to avoid this, we just prohibit the digits 2 everywhere. And by doing this, we avoid this situation. And this is also the reason why we chose the ternary system instead of binary. Because if we didn't have to prohibit this digit 2, then the same argument would work for the binary system. But like it could be that the sequence would end with an infinite sequence of 1 in the binary system it's prohibited. So this this special case would not work. So to avoid this situation, we chose a ternary system and prohibited one of the digits. And by doing this, we avoided this situation. Okay, so basically that's it.